Not all soils are created equal, and if it weren't for chemistry, we wouldn't be able to grow many crops here, nor here, nor here. It's like this. Soils are composed of sand, silt, clay, and organic matter. Some have more sand, others more clay. Each soil's unique blend determines its color, texture, and storage capacity for nutritious chemicals. Although incredibly small, nutrients still need their space. And by space, we mean the area surrounding the soil's tiny particles. Keep in mind that surface area is not the same as particle size. For example, clay particles are tiny compared to sand, but they have more than 1,000 times as much external surface area as the particles in an equal volume of sand. However, if a nutrient just sits there unattached, it will likely leach out from the soil when it rains and will not be available for plants. Remember that time when you rubbed a balloon on your best friend's hair and stuck it to a wall? Well, a similar phenomenon occurs in the soil. Through their electrostatic energy, nutrients cling on to clay particle surfaces. Nutrients like calcium, magnesium, potassium, and ammonium are all positively charged chemicals, or cations. And as it turns out, most clay particles and organic matter in soil are negatively charged. So, many nutrients are positive and particles are negative. Perfect. In chemistry, as in romance, opposites attract. Good. No more leaching. But like the balloon on the wall, the nutrients are only temporarily held. In fact, there's actually a shell of water molecules that forms around the cation, preventing it from bonding permanently. This shell is often called a hydration sphere. If a plant wants a nutritious cation like potassium, it will need to exchange it for another cation or cations of equal charge. Luckily, plants produce hydrogen cations that they can exchange. One hydrogen cation for one potassium cation. Easy enough. But for nutrients with a positive charge of 2, like calcium, 2 hydrogen cations are needed. The higher the positive charge, the harder it gets to exchange or trade cations. That's because a cation with high positive charge and small size is preferentially held by the soil over those with lower charge or larger size, meaning that a large cation with a positive charge of 1 will be the first to be released. A divalent cation, having a charge of 2, will be released more easily than a cation with a positive charge of 3. Whether they are held tightly or not, the nutrients are available to the plant in exchange for other cations. Not all nutrients are cations, however. Some are actually negatively charged compounds, or anions. Since anions, like nitrate or sulfate, have a negative charge, they are unable to attach themselves to negatively charged particles and, as a result, leach out when watered. Of course, all soils are different. There are soils in the tropics, for example, that have positively charged soil particles. And in that case, it's the anions, not cations, that are held temporarily and then exchanged with other anions. Most soils, however, have negatively charged particles. The more negatively charged a soil is and the more surface area a soil has, the more cation exchange capacity it has. This is such an important factor for plant growth that scientists measure a soil's cation exchange capacity, CEC, in order to help farmers determine how much and how often fertilization is needed. That's because CEC is sort of like a cup size at a fast food joint. Some soils are supersized, but others have a kiddie cup. Pouring too much will just cause a mess, but if you refill several times, you can still quench your thirst. Farming in low CEC soils works almost the same way. Even though the soil has lower capacity, you can fertilize more often using smaller amounts and the plants will grow healthy and strong.